So this little video is about ionic solutions. So you may remember that the activity of a solvent in a real solution, so for solutions that deviate from Raoult's law, is given by an activity coefficient multiplied by the mole fraction of the solvent. For the solute, the equation is the activity coefficient multiplied by the molality of the solute divided by the standard molality, which is typically 1 mole per kg. So this is for all real solutions. Electrolytes, where we have salts dissolved in water, are non-ideal for a large number of reasons, but the biggest reason or the most important reason is electrostatics. So in an ionic solution, or when a salt is dissolved in water, there are cations and anions in solution, and if you plot the attractive force between two particles, this goes as 1 divided by r squared. You will remember that the potential energy of Coulomb's law is proportional to 1 by r, so the force, which is the gradient of the potential energy, will be 1 by r squared. And if you plot this, this will decay something like this. So this would be electrostatic. If you do not have electrostatic forces, you have mostly van der Waals attraction, and here the attractive component of the van der Waals potential goes as 1 by r6, which means the force is proportional to 1 by r7. And this, on the other hand, decays very quickly. So this is for typically van der Waals type of liquids. So even for very dilute solutions, electrolytes deviate significantly from ideality. The second point is that when ions coexist in solution, it is difficult to calculate the activity coefficient for them separately or individually because they are very close to each other and are always interacting. So what do? We define what is called a mean activity coefficient. So let us try to quantify this. Let's say you have a salt Mx, which when dissolved in water gives you a cation and an anion. If you write the molar Gibbs free energy for this salt, you will have the standard potential for the cation plus RT logarithm of the activity of the cation, and you will have the same term for the anion. Since the activity is given by this equation here, we can rewrite this as ln of the activity coefficient of the cation multiplied by the molality of the cation divided by the standard molality, and you will have an identical term for the anion. One can now separate this, remembering that log of A by B is equal to log A minus log B. If you do that, you get standard chemical potential of the cation plus RT log molality divided by standard molality plus RT log of the activity coefficient of the cation. That's one term, and you get a similar term for the anion, but here you have the activity coefficient of the anion. This term and this term can then be combined to form this combined term, and then the product of the activity coefficients of the cation and the anion can be written as the square of what is called the mean activity coefficient. So the mean activity coefficient is the geometric mean of the individual activity coefficients of the cation and the anion. If gamma plus gamma minus is written as gamma plus minus squared, and this 2 can eventually come out of the logarithm here, then you have two of these terms. One of the term can go here, and the other term, I'm sorry, not here, here, and the other term can go here, the other term here, and what you get finally is molality of the cation multiplied by the mean activity coefficient divided by the standard molality plus molality of the anion, chemical potential, standard chemical potential of the anion plus RT log molality of the anion multiplied by the mean activity coefficient divided by the molality. So this is how you would write the molar Gibbs free energy of an electrolyte, assuming of course that it's a simple case where mx goes to m plus x minus. You can have more complicated cases. For example, if you have a compound like MpXQ going to P moles of M plus Q moles of X minus, then this equation will be slightly modified and will be equal to P multiplied by the first term here mean activity coefficient divided by the standard molarity plus Q, and the same term, similar term for the anion. In this case, the mean activity coefficient, and this can be shown, will be equal to the activity coefficient of the cation to the power of P multiplied by the activity coefficient of the anion to the power of Q, and the whole thing to the power of 1 divided by P plus Q. So, for example, if you have a salt like magnesium phosphate, then gamma plus minus will be equal to gamma plus the activity coefficient of magnesium to the power of 3 multiplied by the activity coefficient of phosphate to the power of 2, and the whole thing to the power of 1 by 5. So now you have a method to calculate a quantity called the mean activity coefficient. There are a couple of notes that we should know. First, the deviation from ideality is now shared equally between the negative charge, the anion, and the cation in the form of gamma plus minus, right? So if I were to plot the mean activity coefficient versus molality, and the activity coefficient can go all the way from 0 to 1. Let's say molality goes from 0.1 all the way to 0.6. It can be shown empirically that these curves look somewhat like this for different salts. I said empirically, so how do you measure this? You can measure the mean activity coefficient from one colligative properties, so the depression in changes in melting point and boiling point, and as you will see in your lab from electrochemistry. So these are empirical ways to calculate the mean activity coefficient. In the next part of this video, we will look at the Debye-Huckel's law, which provides a physical interpretation of the non-ideality